This is lesson 5.2 on systems of linear equations, elimination. The last time we introduced this idea of a system of equations, we said that a system of equations is going to be a collection of multiple equations, and that a solution to this system is going to be some collection of values of our variables that make all of those equations true. Now, we specifically looked at linear equations. We mentioned that even though a linear equation, when we're dealing with two variables, is a line, when we introduce 3, 4, multiple variables, we're talking about a simple shape, but it's no longer technically a line. We're going to primarily focus on the case, though, where we just have two variables. So our linear equations in two variables do, in fact, describe a line. And thinking about this geometric interpretation of these equations is actually helpful, because if we have a system of linear equations with two variables, that means that we have a collection of multiple lines. A solution to the system is going to be where those lines intersect. So if there's a point that makes an equation true, that corresponds to a point on the line. So if we can find a point or multiple points that are on the lines when we're dealing with a system, that's going to be a solution to the whole system, because that's going to make each equation true. Now, when we have two equations in two variables, we only have three possibilities. One possibility is there's going to be exactly one solution. This is going to be the case that we encounter the most. So the leftmost picture describes what's going on there. When we have exactly one solution, we say that we have an independent system. So this corresponds to two different lines at two different angles that intersect at a single point. So an independent system is going to be the most common one that we encounter, but it's not the only possibility. Another possibility is, what if it turns out that the two lines that we're working with actually describe the exact same line? It looks different, but in fact it's the same line. When that happens, we see that we are dealing with a dependent system, so that we have an infinite number of solutions. Any point on that line is going to satisfy both equations, because, surprise, surprise, it's the same equation. So anything that will satisfy one will automatically satisfy the other. So we denote that with our picture here as just a single purple line. So the red line and the blue line are actually right on top of each other. And the last scenario is what we call an inconsistent system. What this means is that we have two lines that are parallel. So we know that two parallel lines never intersect. So if our two lines do not intersect, that means that we cannot have a solution. So there's no way that both of them are going to be true. So those do pop up fairly frequently, actually, but we're actually not going to see them all that often. Once again, what we will encounter most of the time are independent systems, where there's exactly one solution. But I do want you to be aware about these other two possibilities: dependent systems and inconsistent systems. Now, when we up the number of variables, when we talk about 3 variables, we said that those correspond to planes. 4 variables correspond to something that we'll sometimes call hyperplanes. So on and so forth. Even though the pictures become a little bit more complicated, a lot more complicated, they still fall into these 3 categories. They're either going to intersect at a single point, intersect at infinitely many points, or not intersect at all. So we still have these 3 base cases: independent systems, dependent systems, and inconsistent systems. Now today we're going to focus on a technique for solving systems of linear equations that lends itself to solving systems of more than one variable quite a bit more easily than our substitution technique did. So what we're looking at today is called elimination. The point of elimination is to eliminate one of the variables. And the way that we're going to do that is we're going to multiply one or both or all of our equations, so that between some pair of equations, one of our variables has opposite coefficients. So for example, maybe in one equation we have a 3x, and in the other equation we have a negative 3x. Maybe in one equation we have a 5y, and the other equation we have a negative 5y. So one of our variables we want to have exact opposite coefficients. What we're going to do once that happens is we're going to add the entire equation together. So both equations, the pair of equations we add together, since we have one variable with opposite coefficients, it's going to be eliminated, hence the name. So we'll be left with just one variable. It'll be a nice, simple linear equation. We can solve for that variable. We will resubstitute that back into one of the original equations to solve for the variable that we have not yet solved for. So elimination, generally much quicker than substitution. A few exceptions, but usually it's going to be the better way to go about things when we have to solve systems by hand. So we'll look at a couple of quick examples of what we'll encounter on the drill, and then we'll look at a more complicated example, a system of 3 linear equations and 3 variables that we can solve using elimination. So let's take a look at this problem. So solve the system 3x plus 4y equals 6 and 2x minus 4y equals -1. Now notice the way that this is set up, we already have one of our variables with opposite coefficients. So we have a plus 4y here and a minus 4y here. I will do that for you for the drill problems. So be on the lookout for that. The drill problems where I intend for you to use elimination, this will always already be set up. So that will make the process much, much quicker. For substitution, you won't see that, but if you choose to use elimination to solve the problems intended, where you're intended to use substitution, that's perfectly fine. Just do it correctly, make sure you get the right final answer, but I won't be looking at your work, so you can use whichever method you want. But it will be, in my opinion, slightly easier to use substitution for the problems where I intend for you to use substitution, and elimination when I intend for you to use elimination. The instructions won't specify, but you can just tell from looking at it. Again, the giveaway here is that notice our y's have opposite values already. So what we're going to do, just go ahead and add them up. 3x plus 2x is 5x. 4y minus 4y is 0. And then 6 minus 1, that's going to be 5. So 5x equals 5. So x equals 1. And then to get my y, take this x, plug it into either equation. It doesn't matter which one. I'm a creature of habit, so I'm probably going to put it into equation 1 9 times out of 10. So 3 times 1 plus 4y equals 6. So that's 4y equals 3. So y equals 3/4. So our final answer is going to be 1, 3/4. All right, let's try another one. So here's another system where we see a big indicator that elimination is going to be the way to go. So notice that our x's this time have opposite coefficients. So let's add everything up. Negative 2x plus 2x, those cancel out. 8y plus y, that's 9y. 1 plus 3 is 4. Divide by 9. My y is equal to 4/9. And once again, to find my x value, I'm going to take this and substitute it back into one of the 2 equations. So I'm just going to, again, put it into the first one. Negative 2x plus 8 times y, so I'm going to put in 4/9 equals 1. So I have negative 2x equals, so I'm going to subtract. Let's see here, this is going to be 32/9, and 1 I know is going to be 9/9. So 9/9 minus 32/9, I think that's going to be negative 23/9. Then I divide both sides by negative 2, so it's going to give me x equals 23/18. The negatives cancel out, making this positive. So my final answer is going to be 23/18, 23/18, 4/9. Now when we get nice final answers, that's nice obviously, but don't freak out when you get weird rational things like this. Now if you get square roots to pop up somehow, then yeah, something has gone terribly wrong. So don't expect that to happen, but weird rational numbers, that's actually par for course. So let's complicate things a bit. What if we introduce another variable? So generally when we have multiple variables, most of the time we're going to have the same number of linear equations. Now not always, But when we're expecting to get just a single point back as our solution, that's generally what we're going to expect. We're going to have just the same number of equations as we do variables. So here we're now working with x, y, and z. So we see that we have 3 equations. So I'm going to label these equation 1, equation 2, and equation 3. Now we don't have any experience working with equations in 3 variables, so we want to get back into terms of 2 variables as quickly as we can. And the way we're going to do that is by using elimination. So what we want to do is look at our equations, see if there's an easy way to eliminate one of our variables, looking at any pair of equations. And looking at equation 2 and 3, I see that my y coefficients are already opposites. So I'm going to add equations 2 and 3 together. So equation 2 is 2x plus y plus 2z equals 6. And equation 3 is x minus y plus 3z equals 6. So I add those up. 2x plus x, that's 3x. X minus y, those cancel out, but that was the point. And then I get plus 5z equals 12. I'm going to go ahead and label this equation 2. I'm going to label this A. The original equations, I'm going to use numbers. The intermediate equations that I'm going to get, I'm generally going to use letters. You don't have to, but that's the system that I adopt to help keep things straight in my mind. Okay, so we have added equations 2 and 3 to eliminate our y variable. So what we want to do is look back and find another way to eliminate our y variable. We can't eliminate a different variable, and we can't use the same pair of equations. That doesn't count. So we can't just add 3 to 2 instead of adding 2 to 3. They're the same pair. You're not fooling anyone. So pick a different pair. And looking at it, I think, notice that 1 and 2, y is very close to having an opposite coefficient if I just multiplied equation 2 by 2. So I'm going to do that. Take equation 2 and multiply it by 2. So everything in this line I'm going to multiply by 2. So that's going to give me 4x plus 2y plus 4z equals 12. And as I said, I'm going to add equation 1 to that. So 3x minus 2y plus z equals negative 4. All right, add up each of these. 4x plus 3x, that's 7x. 2y minus 2y, those cancel out. But again, that was the point. 4z plus z is 5z. And then 12 minus 4, that's going to be 8. I'm going to call this equation B. All right, so I now have a system of 2 equations in 2 variables, equations A and B, that are both in terms of x and z. From this point, pick your poison, basically. If you like to use substitution, feel free. If you like to use elimination, feel free. I generally prefer elimination. It just seems to me to be a much quicker way of solving the problems. So notice my z's are the exact same. So let me multiply b by negative 1. So negative b, that's going to be negative 7x minus 5z equals negative 8. Then I'll add equation a to it. So just leave it alone. 3x plus 5z equals 12. So when I add these up, negative 7x plus 3x, that's going to be negative 4x. Negative 5z plus 5z, that's going to cancel out. Then negative 8 plus 12, that's going to be 4. So divide both sides by negative 4. I get that x is negative 1. Now, just like with our systems of equations with 2 variables, we shouldn't necessarily freak out if we get a weird rational number here. However, for the application problems, if we get a weird number here, that's going to make life just very unpleasant for us. So I am more inclined to make sure that these particular problems work out nicely, but know that out in the real world, they're not guaranteed to do that. World's a tough place, but I'm going to look out for you here. So expect nice numbers here. If you're working through this and you get negative 17 over 9 back, I'd say double check your work. You may have made a silly mistake somewhere. Okay, so we've found our first variable. We know what x equals. We've got 2 to go. We need to find what z and what y equals. What we're going to do next is to take this value, plug it back into one of our intermediate equations. Plug it back into A or B. It doesn't matter which one. Take your pick. I like A. So let's see here. Plug this into A. So that's 3 times negative 1 plus 5z equals 12. So 3 times negative 1, that's going to be negative 3. So I'm going to add 3 to both sides. That gives me 5z equals 15. Divide by 5, that gives me z equals 3. All right, 2 down, 1 to go. I've got my x, I've got my z. All that's left now is my y. To find my y, you guessed it, I'm going to take my x value, my z value, plug it into one of these 3 guys up here. Once again, it doesn't matter which one. I usually take the one that comes to me first, so I'll go with equation 1. So 3 times negative 1 minus 2y plus z, so 3 equals negative 4. So negative 3 plus 3, hey, that's lucky, they cancel out. So I have negative 2y equals negative 4. Divide by negative 2, y equals positive 2. So my final answer then, remember with our system of equations with 2 variables, we wrote our answer as an ordered pair. Here we're going to write it as an ordered triplet. So we're going to put our x, comma, y, comma, z. So our final answer is going to be negative 1, comma, 2, comma, 3. Now the reason we like thinking about these in terms of ordered pairs, remember how we talked about how the solution to a system of linear equations in 2 variables we can think of as being the point where 2 lines intersect? Well, this is the point where these 3 planes intersect. Now we aren't accustomed to thinking in 3 dimensions, so as oddly as that sounds, let me rephrase that. We're not accustomed to thinking about mathematical shapes in 3 dimensions. So visualizing what the intersection of 3 planes at a single point would look like might make our head hurt a little bit. That's okay. It's interesting to think about, but it's not vital here. I'd encourage you to try to visualize what would that look like if three planes intersected at a single point. We can talk about that in person if you like, but it's not a requirement. You don't need to be able to visualize that to solve solve this particular problem. But here, in fact, what we've said is true. These 3 things describe 3 separate planes, and those planes all intersect at this single point, negative 1, comma 2, comma 3.